Electric and hybrid vehicles are making headlines around the world as manufacturers move to new technology to respond to changes in legislation, reducing the environmental impact of their vehicles and machinery. Electric vehicles have four key powertrain subsystems: the battery system, the traction motor, power electronics, and the thermal management system. Everyone normally thinks about the electric vehicle battery system, but there's all the other components like the motor and the DCDC and the onboard charger, and lots of opportunity to take weight and volume out of the driveline in those components. In this video, we're going to look at these key power electronics subsystems and talk about their function, the key design challenges, and the technology trends. The traction inverter takes the DC electric supply from the battery and converts it into a controlled, usually three-phase AC output to drive the traction motor. To do this, we have a controller which operates an array of switching devices known as a full bridge. The key elements of the inverter are the controller, gate drivers, switching devices, and the DC link capacitors. The onboard charger converts AC supply from the mains grid into DC to charge the battery. There are a lot of similarities to the inverter function, except the charger has more electromagnetic components inside it. Finally, the DCDC converter steps the high voltage DC from the battery down to a safe level for the vehicle ancillary systems like the radio and lights. In order to step the voltage down and safely isolate it, the high voltage DC input is converted from DC to AC using switching devices, then stepped down over a transformer and rectified back to DC again. Across all the devices, the key components are the controllers, switching devices, gate drivers, and capacitors. And in the onboard charger and the DC-DC converter, the electromagnetics are also critical. Design trends are for smaller, more efficient devices to deliver improved vehicle performance.
A lot of the big challenges with power electronics is the whole packaging of the system, and where it stops being this sort of abstract electronics problem and becomes an actual physical mechanical problem where you have to bolt some bits together and solder some parts together. I heard a phrase a couple of years ago, and it's something that's always resonated with me, and someone described it as multi-physics integration. Right. And I think for power electronics, it really is the sort of the heart of the challenge for power electronics. We have to think about the electronic components that we choose and design, and the sort of shape and the size of those, and how they're going to be integrated together. There's obviously the thermal aspects that we talked about. How we're going to cool that transistor, how we're going to get the heat out of that small area and into the water or the air, depending on the cooling method we're using. And similarly for things like magnetics, even with some of the higher currents and higher powers, even the buzz bars themselves might need cooling and attaching to the cooling system in some way, because to get the size down, the current density goes up. We actually have to start thinking about the temperature of buzz bars as well. So, and then we've got all the things that go with more the electronics side of things. So we've got the EMC. Think about, and as I said, higher switching frequencies, higher switching speeds, loop inductances, parasitic capacitances, all become even more important and have to be considered carefully. And especially when you're working with the high voltage, you've also got all the creepage and clearances to deal with as well. So you always end up with this sort of conflict and compromise where you're trying to keep things really close together to reduce parasitics and inductances, but you've got to deal with the high current density and the creepage and clearance distances as well. We're seeing the trend moving towards higher voltage traction batteries. Right. So a lot of the sort of passenger cars on the market are running with around 400 volt batteries. Right. We're now seeing a move from OEMs where they're wanting to run more like 800, even 900 volt battery systems.
Right.
And that's obviously the battery charger, the inverter and the DC-DC converter all have to start to deal with that higher voltage systems.
Improving the cost and performance of electric and hybrid vehicle powertrains requires smarter, more highly integrated power electronics systems. There is also more customization for specific vehicle applications as a result. The additional development costs being repaid quickly in savings at a system level over the higher production volumes now being achieved by electric and hybrid vehicles. The need to reduce packaging weight and volume is driven by the desire to improve overall vehicle performance. A lighter powertrain will use less electrical power to move and therefore delivers an improved range from the battery.
We are focusing on, within AVID, is we're looking at the use of silicon carbide devices,
Right.
which are still fairly new to the market. The supply chain is catching up rapidly, and the suppliers of those components are putting a lot of effort into getting those devices into maturity, and also bringing online automotive standard devices and modules to support that.
Right.
The benefit that they offer is that we can switch at a much faster rate, so we have reduced switching losses in those devices, much more efficient,
Right.
but also that we can switch them at a higher frequency as well because of those reduced losses. That increased DVDT and DIDT that we get from the higher switching speeds has that knock-on effect of overshoots, so any sort of parasitic capacitances and any sort of loop inductances that we have to, that's gone to another level, the care and attention that we have to take in the packaging and the componentry that goes around the main switching transistor to create the power converter. So I think the main driver is inefficiency. So and all the benefits that come from that reduced losses. So some of the silicon carbide devices can claim up to like a 70% improvement in efficiency on the transistor itself, which obviously has the knock-on effect of we can have a reduced coolant plate, reduced size there. So and the coolant plate usually can attribute for a quarter to a third of the size and weight of the overall device as well. So we can see big benefits in a more efficient transistor, so less cooling requirements to get that sort of equivalent performance that we have with IGBTs.
Right.
The other effect is the being able to run at higher frequencies. Obviously things like magnetics, transformers, there's size and weight benefits there as well that we can obviously run with a high frequency transformer, be much smaller than we would have it maybe 5-10 years ago. Things like the battery charger and the DC-DC converter, the topologies are a bit more complex than the traction inverters.
Right.
So the actual silicon carbide devices probably represents a slightly smaller portion of the overall system cost.
Right.
We have more. There's more magnetics. There's more capacitors and other componentry in the DC-DC and the battery charger that you don't necessarily have in the traction inverter.
Right.
So for the DC-DCs and the battery chargers, I think that overall benefit are worthwhile, even with the increased cost of the device themselves. On the traction inverter, it's slightly different case. I think the switching device is a much bigger proportion of the overall cost of the system.
Right.
We've got no output magnetics; they're all in the motor.
Yeah.
So it's pretty much the switches and a decoupling capacitor. That's a bit simplified, but
5-minute job.
Yeah, how hard could it be?
Yeah.
But yeah, I think in the traction inverters, maybe jury's still out a bit. But definitely see, there's more and more devices coming on the market as we speak, and I know some some companies are actually, accelerating that that time to market for their devices, because they see that there's definitely a pull from people like AVID and also the OEMs to start to use that technology.
Right. And functional safety plays a huge part in the design process now, doesn't it? I mean, it's almost in some ways the power electronics hardware bit is kind of is a smaller part in the overall design process than actually delivering the sort of higher level functional safety requirement.
Yeah, it does to quite a big extent, but I mean our general engineering process is still that. I always like to maybe oversimplify it a bit, but we define what we want the thing to do.
Yeah.
We design it.
Yeah.
We analyze it to make sure that what we've designed meets the requirements.
Yeah.
We then build it.
Yeah.
And then we test it to validate that it meets what we require it to do. So that basic sort of engineering process is always there, and always will be. But
yeah.
A lot of the stuff that we're seeing around functional safety, a lot of it is to formalise that process.
Yeah.
Make sure that any requirements that are captured, that we have got that clear validation through analysis and calculation, and then verification through test, and to make sure that all lines up, and that the device that we produce is doing what we intended it to do and what it's been designed to do.
Right.
And then part of that requirements capture and that sort of tracking and tracing of those requirements is looking at those sort of functional safety goals that we would try and define up front at the start of the project, and how this device contributes and fits in with the overall safety goals of the vehicle and the platform that it's targeted for. As you know, we always work very closely with the OEMs and the vehicles, the project teams of the vehicles that the devices are targeted to. We always want to be collaborative and work together with OEMs and make sure what we are delivering is exactly what they want and fits in with their system.
Yeah.
We need that sort of multidiscipline team as well to all work closely together.
Right, yeah.
And to be able to quite quickly look at those compromises. Where can we make that trade-off, and then very quickly evaluate whether it's worth it or not. So okay, we could use this device, but it means that this is it's easier to cool. It makes this interface more reliable, more robust, easier to manufacture.
Yeah.
But it's twice as expensive as this part, which but having all of those sort of disciplines who can very quickly we can all have our input into that problem and very quickly come up with solutions. It is really useful having all those people co-located.
Right. We hope you have enjoyed this brief overview of the key power electronics systems in electric and hybrid vehicles and the design challenges and trends. If you would like to learn more, contact AVID today to find out how we can help you deliver your electrification program.